one of the definitions of the dot product had something to do with the angle between them and the cosine of that angle. And so this, for us, finds a way to find angles between two vectors by solving for theta. If we're given u and v, we can use the algebraic definition to compute the dot product, and then we can find magnitudes now, and then just get the cosine inverse of that. Then you'll be able to find your theta. So turns out with a cosine function, there's an important angle here that gives an important consequence for the dot product. You know what I'm thinking of? You know what I mean when I say that? Do you understand what I said? There's a special angle here that would make this dot product equal to something. Is that better? What? 90 degrees. Whoops. So an important consequence that we'll be using a lot is the fact that if you have two vectors that are perpendicular to each other, then the dot product is equal to 0. Okay. So if theta equals pi over 2, i.e. vectors are perpendicular, so the angle between them is 90 degrees, then u dot with v, or u dot with v, equals 0. So this is an important result that we have for the dot product. Okay. Now, there's a couple more in my list of important geometric properties or special geometric properties, and one of them has something to do with the angle being bigger than pi over 2. So the next important piece of information would be if the angle is greater than pi over 2. So if the angle is greater than pi over 2, what kind of angle is that? Is there a name for that? You know the name for that? Obtuse. So if the angle is bigger than pi over 2, they call it obtuse, then the dot product is going to be, you know how the cosine is positive from 0 till pi over 2, and then past pi over 2 to pi, it becomes negative. So in this case, when you have an obtuse angle between the two vectors, or when your two vectors are obtuse, then the dot product is less than 0. It's negative. Okay? So it's a scalar, right? So we could talk about positive and negative numbers from that scalar. And then one more piece of information that would be useful is that if the angle was 0, then according to the geometric definition, what's the dot product going to equal? What? The magnitude of the two vectors multiplied together, right? So that might not seem that big of a deal or that important, but if we change the idea, instead of just saying the angle between zeros, what if we actually have the same vector? You dot a vector with itself. So that's another important piece of information that we can use sometime later. So if the vector is dotted with itself, we think about it as having an angle of 0. And cosine of 0 is 1. So u dot u is equal to the magnitude of u times the magnitude of u times 1. So it becomes, the dot product becomes the magnitude squared, which may not mean so much right now, but in terms of trying to prove things later on, it may come up as something that might be handy for us. And we may refer back to this idea, this fact, later. Okay? So those are the special cases for our dot product, and we're using that geometric definition. Well, actually, we're kind of using the combination of the geometric definition and the algebraic definition, so it helps us. Any questions? All right, let's take a look at a couple of other important properties for the dot product, and we'll take a look at some applications. Let's see. Some other important properties for the dot product. I believe this is listed in your book the same way. And we can label these if we want or say comments about it. The first one is saying that it's commutative. But the order doesn't matter. We kind of saw that in the algebraic definition. And you can also see it in the geometric definition. Just by changing the order, you're just changing the order in the multiplication. And we know that multiplication is commutative, so that's not that big of a deal. This isn't quite associativity, but it's saying if you take the dot product of something and then you scale it, it's like scaling one of those vectors. Not both, but just one of those vectors. And then the last one is a distributive property, just like the distributive property of multiplication. And so you can think about distributing. Now, the middle one is kind of like associative, but it's not formally associative. If we were to try to see if the associative property works for dot products, I would have to remember how associative property looks like. You have three things that you're multiplying or adding, and then you group them up two at a time. So let's see if that would make sense. Can we do an associative property for the dot product. This is U dotted with V dotted with W, and then maybe we group two of them at a time. The question is this true? What do you guys think? Any ideas? Yeah?
Isn't it if you dot two vectors you get a scalar?
Yeah. Good job, Sirius. Isn't it when you dot two vectors you get a scalar? Imagine dotting these two things, then this becomes a scalar. And now you have a scalar dot a vector, which doesn't make sense. If it was a multiplication, scalar times a vector, then that's scalar multiplication. But this is dot product we're trying to define here. So, no, this can't work because a dot product gives you a scalar. So it can't work. So the original associative property as we know it wouldn't work for something like this, for this case. Okay? But it's still commutative, still distributive, so we're still okay with those properties. Any questions? All right, let's move on. I think now we're ready for some applications. And we'll start with an application of defining a plane in 3 dimensions. So this is where it becomes, you have to try to visualize things. And this is, I'm not, I think the book does it this way, which is why I'm including it here. Probably, for me, I wouldn't want to necessarily include it here while we're still talking about dot products, but trying to present it the way they're doing it in the book. But for us, this will become important to come up with an equation of a plane. Just like in algebra, you learn about the equation of the line, and then you memorize this y equals mx plus b business. You try to figure out where the m and the b and all that stuff come from. The equation of a plane kind of follows the same way. Maybe I should have started with the equation of a line first, but let's go with this for now. So if you imagine a plane, just look at your desk, and if you imagine what we might call as a normal vector, you can imagine a perpendicular vector to your desk, right? Perpendicular vector. Now, the size of that vector doesn't matter, and it doesn't matter if that vector is going directly above your desk or pointing downward. As long as it's perpendicular, that's what really matters. So what we're trying to say here is that a normal vector can more or less dictate the direction of your plane. So if you're imagining that normal vector and you rotate that normal vector then a little bit, then it's not going to be normal anymore, right? I don't know what I'm trying to say there. Let's see if I can illustrate what I'm trying to say. So if you take your vector and rotate it a little bit, then it's not perpendicular anymore. That means you actually have to take your plane and rotate that as well to make it look perpendicular. So your normal vector, regardless of where it is, kind of dictates the direction of your plane. So the only other thing you need is a point. Let me go back to the whole idea of a line again. Back in algebra, or even when we were doing lines in your quiz, when you were asked to find the equation of the line, what are the two things that you want to look for? A slope and a y-intercept, or a point. A point and a slope would help you find the equation of your line. So similarly, for this, if you want to find an equation of a plane, all you really need is a point, and our point in this case will be x naught, y naught, z naught, and a normal, which is kind of like your direction. I wouldn't call it your slope, because a slope is just one number, and I wouldn't even call it direction, because it's actually opposite, it's perpendicular to the plane, so it's not really a direction, but we can think about it as some sort of directional thing. So the idea behind this equation is that if I take any random point on the plane, and I'll call this point x, y, z, any random point on the plane. So this is arbitrary. Arbitrary means random. General point that describes any point that's on the plane. Your x naught, y naught, z naught is some fixed point on the plane. And then your n is normal to the plane. So how do you suppose we can create an equation here taking advantage of the idea that the dot product of two perpendicular vectors is 0? Do you understand what I'm asking? How do you suppose, with just a point and a normal, that's all I have, and then now I kind of came up, I pulled this out of the air, just some arbitrary point, as long as it's on the plane. How can I come up with an equation using the dot product and the fact that the dot product of two perpendicular vectors is equal to 0? Any ideas?
Well, can't we say that the arbitrary point is a vector from the base normal vector to that point?
We could do that, but we don't necessarily have to. So I think maybe that's where you were going, Lauren, but
And then you dot that vector.
what if we do what Cameron said and create this vector from the arbitrary point to the fixed point? Right? So let's do that. What would this vector be? Do you remember how to make a vector from 2 points? Just subtract, right? So x minus x naught, the head minus the tail, x minus x naught, and then the y components, y minus y naught, and then the z component, z minus z naught. And the fact that Lauren was saying, what if we move it to the tail? Well, it doesn't matter, because remember, these vectors can move around any way we want, right? As long as they have the same direction and same magnitude, they're the exact same vector. So what if we move that over here, and then the dot product of this, these two things should be perpendicular. So then the dot product should be equal to 0. So let's dot them. Let's dot our n, dotted with this vector that we just found, this vector, we'll call it v. That's supposed to be equal to 0, because regardless of where the point is, look on your desk, draw a point on your desk. Well, maybe just imagine a point on your desk. as something that's fixed, and then draw another random point on your desk. If you get your pen or pencil and connect those two vectors, those 2 points, that pencil will be on your desk. That's your V vector. And now take another pencil that's perpendicular to that. That's going to be normal vector. So regardless of where you move that normal vector, and regardless of where this V vector is, they're always going to be perpendicular to each other. So what do we have? We have N, which is ABC, dotted with this vector x minus x naught, y minus y naught, z minus z naught. That's supposed to be equal to 0. And if you actually perform the dot product here, it becomes a scalar, right? The dot of two vectors is a scalar. So we'll say A times x minus x naught, B times y minus y naught, plus C times z minus z naught, and that's equal to 0. That's your formula for your equation of a plane. Now this can be rewritten, it says here, as ax plus by plus cz is equal to d. I wonder what d is equal to. Any ideas what d is equal to? Let's figure out what d is equal to. It looks like these are all scalars, so I'm just doing regular algebra back like what I did in, when did you do algebra? Kindergarten? In preschool? Whenever you did algebra. You would FOIL this out, right? Or distribute. AX minus AX naught plus BY minus BY naught plus CZ minus CZ naught is equal to 0. Now let me just focus on what I want my left-hand side to be, and imagine taking everything else over to the other side as my right-hand side. So everything that I circled there that goes on the other side is negative, so when I bring it to the other side it becomes positive. So you got AX plus BY plus CZ is equal to AX naught plus BY naught plus CZ naught. And that will serve as our, that can simplify and it will serve as our D value. It's just a scalar. A, B, C are given, x naught, y naught, z naught is given, so imagine that. Let's take this a step further. These two sides look awfully alike. Tell me what they have in common. They have A, B, and C, right? Looks like it's written neatly there. Oh. Written neatly. If you can read my handwriting. So A, B, C there. And then the only difference is the x, y, z on one side, x naught, y naught, z naught on the other side. Now, imagine, can you rewrite this as something else? You understand what I'm asking? I don't understand what I'm asking yet either. Let me ask it differently. Is this a result of something that might have, Jesus said that he saw A, B, C in both sides, that might have, wait, A, B, C is N, right? So is this something that maybe I can somehow rewrite that would have an N in it instead of an A, B, C? Ah, that's a better question. Now you can answer it, right? What do you guys think? N and what?
The unit vector.
No, not quite. What? N in the knots? The knots? That would be on the other side, right? N in the knots. What do you mean N in the knots? What? What? Wait. What? What am I missing? The other side? What am I missing? Dot. Isn't it just ABC dotted with XYZ? That sounds like a song. Isn't this ABC dotted with X naught, Y naught, Z naught? So go backwards, go forwards. Now it's really sounding like a song. ABC, XYZ. Easy as 1, 2, 3. Forwards and backwards. Now you got a square dance going on, or a plane dance. Ooh. So now what we're able to do is we're able to rewrite the equation of a plane as a dot product of some vectors. So we might see this form every once in a while. And when you see that form, you have to try to remember back to this day and time in your life where you saw it. How are we gonna remember it? A, B, C, X, Y, Z, forward and back, 1, 2, 3, forward and backwards. All right, I'll try to remember that. But you have to try and remember that too. So sometimes we let X equal to X, Y, Z. I'm noticing my parentheses changed from square, these alligator brackets, to parentheses. And I think I had asked permission already earlier that I can switch notations like that. So I won't. So sometimes you see a boldface X in the book. That just means its variables X, Y, Z, or X, Y, depending on what dimension you're living in. And sometimes you'll see X naught as a boldface vector in the book, and that means you're looking at X naught, Y naught, Z naught. So that just means that this can be rewritten as N dotted with X and N dotted with X naught. And that, the right-hand side, is actually your D, your scalar D. Okay? So if you're wondering how to write an equation of a plane, looks like it's just a couple of dot products. All you need is a vector, a normal vector, and a point on the plane. Once you have that, it becomes a formula. Suppose we should do a quick example. Let me see if I have a homework type of problem that we can do real quick. Oh, I didn't prepare my student view. Just enter. see what kind of problems they have here in this section. Oh, this is a cross product already. Ooh. Let's go back. Wow, we're still on 12.3. So we can just jump to find the easy way of finding the equation of a plane. But I'm hoping you walk through this information and see how all that stuff happened. Where is it? They don't have it. Direction, scalar projection. They don't have it. Maybe it's coming later. All right, well, let's just make one up then. All right, let's do an example. Let's make up a vector that this plane is going to be perpendicular to. Find a plane with normal vector n is equal to, now let's come up with a normal vector. Draw 3 numbers. 1, 2, 3. Yeah, it's creative. Normal vector and containing the point what should our point be? No, let's make it a little bit different. 4, 3, 2. Let's make one of them negative. Let's make the 3 negative. We can go through the process of setting this up, but I think if we just jump to the formula, it should become fairly easy, I hope. So let's see. According to the formula, the plane equation of the plane should look like this. It should look like n dotted with x, y, z, and n dotted with the given point x naught, y naught, z naught. So take an extra step here that I'm not going to be doing much later. You dot n with 1, 2, 3, or n is 1, 2, 3, sorry. You dot n with x, y, z. And in terms of an equation, when you're coming up with an equation, a relationship between variables, you need the actual variables, so this is where the variables are. And then on the other side for d, you have 1, 2, 3, that's your n, and dotted with your point on the plane. So the dot product is just going to give you 1 times x plus 2 times y plus 3 times z. So that's your ax plus by plus cz on the left-hand side. And on the other side is your d. So 1 times 4 plus 2 times negative 3 plus 3 times 2. This is 4 minus 6 is negative 2. Negative 2 plus 6 is positive 4. Is that right? 4? right? So that's it. That's your equation of the plane. Then you're done. Any questions? So a section a little bit later on in this chapter will talk about more lines and planes business. So we'll get to know these things. But this is a good application for the dot product. The equation of the plane actually comes from the dot product of two vectors. All right. Let's take a look at another application for the dot product. Scalar projection. So the idea behind a scalar projection is to take two vectors and then take one of them and make it drop down to the other vector, and imagine having a light source right above this. And if you make a light source right above this, you can see a perpendicular distance over here. So this length is what's called a scalar projection, the projection of one vector onto the other. So they call it COMP. I don't know, I think that's what they call it in the book, because that's sometimes referred to as a component projection. There's another one called a vector projection, which they use PROJ, proj. But when you see this, this is the scalar projection, which means the result is a scalar, and we're looking at really that length or that distance. Now, we can do some math to figure this out. I suppose if we imagine looking at this length over here, this is what we're looking for. Let's call that x or something. And then let's call this vector, well, what's the length of this red line over here? Any ideas what this length is? I want to basically, I don't know if I want to make Pythagorean's theorem. Well, let's just see. What is this length over here?
The magnitude of V.
Magnitude of V. Right? So let's see. If I want to figure out what x is, that's the adjacent side. Hey, I can use what's that called? I have adjacent and the hypotenuse. I can use a cosine, which means I'll probably need to refer to this angle. So x is equal to, well, let me write it in terms of the cosine first. Cosine of theta is equal to the adjacent over the hypotenuse, which is magnitude of V, right? Let's see, I want to solve for x, because that's the length that I'm looking for. And x is actually equal to magnitude of V times the cosine of theta. What's the cosine of theta? All right, let me move to another page real quick, and let me ask this question again. What's the cosine of theta? If it's perpendicular, it'd be 0. All right, let me highlight this. What's the cosine of theta? So it's a dot product divided by the magnitudes. Okay, that's the definition, the geometric definition that we defined for the dot product. So the cosine of the angle between them is the dot product divided by the two magnitudes. So I have here the cosine of theta is one thing based on what we have, but by the definition, It's a geometric definition. I also know that the cosine of theta is equal to the dot product of V and W, right? Divided by the magnitudes of V and W. So I'm going to go ahead and replace that. So x is going to be the magnitude of V times the cosine of theta, which according to the definition is V dot W over the magnitude of V times the magnitude of W. And you see that the V's cancel. They're scalars, so they just go away. And so here's what you have. That's what x is equal to. Okay. All right, now I said that the scalar projection gives you a scalar value. It gives you the length of this thing. What if I want this vector? Not just this length, but the actual vector. So that part, if I'm looking for this vector, this is going to be the vector projection. Now, describe this vector for me, this vector projection. Should we call it something? Let's call it VW. Let's call it U. Describe U.
It's in the same direction as W.
Same direction as W. That's one important piece of information. It's the same direction as W. Now, the length of U is given by this x value, right? So I want a vector going in the same direction as another vector, but scaled to a specific value, to a specific length, to a specific magnitude. I want a vector going the same direction as W, but scaled. So
Could we do vector v is equal to x times the vector W divided by the magnitude of W?
So x is a scalar. I put an arrow on top. I had to quickly erase it. So this is x is just a scalar. It's given by this thing, right? So x times. Now we don't want to just multiply it by w because that's not going to control the magnitude. So we have to make it into a unit vector. Like Lauren said, we have to take the w and divide by its magnitude. So that makes it into a unit vector. So by multiplying this, you can have it extend to or shrink down to whatever size you want. Okay? So x is equal to this, v dot w over magnitude of w, and we want to multiply this by w over w. So let's just rewrite that a little bit. V dot w divided by w multiplied by w over magnitude of w. Wow, that looks messy. I have a couple of dots here. Can you tell me what these dots are? Do you understand what I mean? Is this multiplication or a dot product? Is this a multiplication or a dot product? It's We could be more specific. Are we multiplying two scalars? Is this a scalar? Is this a scalar? It's a unit vector, so this is a vector. So this isn't just multiplication, it's actually a scalar multiplication. This is M-U-L-T. M-U-L-T, just in case you're having a hard time reading it. Mult. So dot product and scalar multiplication, that's what's happening here. Actually, what we can do is, since this is a scalar also, we can move that to the other side. Move it with a scalar part. So the notation for vector projection is we say proj, P-R-O-J, projection of V onto W. Just like how the component is. This is a scalar projection of V onto W. V is written kind of like the same length, and W, where it's being projected onto, is a subscript. So projection of V onto W. And you'll get a vector out of this. It's a vector W, essentially, that's been scaled with V dot W divided by W squared. The magnitude of W, magnitude of W, W squared. So scalar, oh, what's this dot? Is this a dot product? What is it? It's scalar multiplication, right? Because on the left-hand side is a scalar, and the right-hand side is a vector. Okay? So that's vector projection. Are we good? Probably want to see an example. Let's see if we have some examples here. There you go. Find the scalar and vector projections. Let's try this problem. So we have 2, -1, 0 for A. A is equal to 2, -1, 0. And B is equal to 0, 1, 1/2. So I think it might be easier if we look at it that way. So let's rewrite this as 2, -1, and 6. And B can be written as 0, 1, and 1/2. We want the component projection of B onto A. So that's B onto A. So A is like that W vector, that's where the shadow is going to be. And then we're going to want the projection, vector projection. So this is a scalar projection. Whoops. and this is a vector projection. All right, so it looks like for either formula, we're going to need the dot product of A and B. So why don't we write the formulas down? So the component projection of B onto A is equal to A dot B over the magnitude of A or B. Oh. It's cut in half. I think it's A. It's the subscript. Let's go check it out. Let's check it out. The subscript. So that's a good way to remember. Look at the subscript because that's where it's projecting onto, and that's your like base vector. So we could switch them if we want. It's commutative. So just look at whatever it's being projected onto is your denominator. And this one, the projection of B onto A is the same thing, A dot B. And it's the same denominator as up here, right? Except it's going to be squared. And then it's being projected onto A, so we want it going the same direction as A, so whatever's down here. So letters change, and then the dot product got switched. So be careful. The dot product is commutative, so it can switch around. But when we're projecting onto something, a vector onto another vector, that order is important. All right, we need a couple of things. We need the dot product. A dot B is 2 times 0 plus -1 times 1 plus 6 times a half. So that's 3 minus 1 is 5. No. Did I say that out loud? 3 minus 1 is 2. Wait, is that right?
Yeah.
2. And then we want the magnitude of A. We don't care about the magnitude of B, so we just need the magnitude of A. So the square root of 2 squared plus 1 squared plus 6 squared. So 36, 40, 41, is that right? Check that. All right. Okay, so for the component projection, it looks like it's just going to be 2 divided by square root of 41. So I'm noticing in this particular problem, it doesn't say anything in parentheses, so round off to like 1 or 2 decimal places. So in that case, you want to put the exact answer, and if the exact answer has a square root, make sure you put the square root. The next one, projection of B onto A, so it's the same thing, except we're going to multiply it by the vector A. So for the projection, the vector projection problem, it's going to be 2 divided by 41. The square root of 41 squared is 41. Times multiply it with a vector 2, -1, 6. I think you might be able to get away with putting that exactly into your box if you had this problem. Well, let's see. If it doesn't take, then make sure you maybe you just need to distribute it and see what happens. All right, let's check our answers. We got 2 over the square root of 41. And for this one, we have 2 over 41. Maybe I'll put parentheses around that. Times a vector. So now they want a vector. I'm not sure about if this will fly with parentheses. Or I can use those brackets, right? But let me try to put parentheses and see what happens. 2 minus 1 and 6. And If you're really confident that this is the correct answer and it's not marking as correct, then maybe you might need to change the parentheses into those vector brackets that they have here. They have these vector brackets, or you can use I, J, and K and see what happens. Is there a way to check this? Let's check it. Yeah, always got my fingers crossed. Oh well. Oh, so your answer could not be understood. So let me try. This is where you fiddle around and try the vector brackets instead. Yeah. In any case, I'm hoping that you're getting used to the system, and if they're looking for a vector, arrows on top, boldface or whatever, and everything else that might be happening. All right, one more quick application. Let's see how quick this can go. And the other application is work. I won't say too much about this. Let's just mention that this is some physics applications, and work equals force times distance, and we have that from back in Calc 2, or maybe if you're taking physics now, we have that that equation, force times distance. It turns out that these things work a little bit better if you're looking at it from the point of view of vectors, because you're not just going in one direction in most cases. Well, when you're trying to pull a wagon or something like that, as an example, you have a wagon, and your wagon, you're not pulling the wagon in a horizontal motion. You would have it with a handle going upward with some angle that it's making. So when you have something like that, you exert a certain force by pulling it, and then you want it to travel a certain distance. And so by keeping this constant force where you're pulling the wagon, and then the wagon is moving a certain distance, you've just exerted amount of force, and that force, or that exerted amount of work, and that work is going to be given by the force times the distance that you traveled. So what happens here is the work now is going to be some scalar value, and that's going to be given by a vector of force times a vector of distance that you're moving towards. Okay, so I think you guys had some lab problems that dealt with this. So I'm hoping you remember. I'm not going to do any examples. You can look through your lab again, or look through your textbook and see what they talk about when they talk about this stuff. All right, we didn't quite get to course cross products. So when we come back tomorrow, that's where we'll start off with course products. We have an announcement?
Yeah, we have some STEM announcements. The speaker series is tomorrow. It starts tomorrow. So we have a speaker series. Definitely come. You get extra credit as well for some classes.
It's the credit.
Also, there's this
What?
Guaranteed 3.0
Yeah.
workshop,
In the
which is
syllabus.
every